Okay. Yeah. To introduce the next speaker, it's my pleasure to introduce Dr. Raeesa Ganey, who completed a BSc at Northwest University in 2011. She completed her postgraduate studies in statistics with a BCom honors at University of Cape Town in South Africa in 2012. And she got her MSc in 2014 and PhD in 2019. Her research methods are in the methods of multivariate data analysis and visualization techniques. And for her PhD, she looked at constructing a principal surface biplots that is used for the visualization of objects together with the variables or characteristics that are observed. And she extended the methodology to allow for accurate representation of non-linearity in data, which is a truer reflection of reality. Recently, she became a formal collaborator to a high-dimensional visualization project in the Department of Statistics and Actuarial Science at Stellenbosch University in South Africa. And she has been employed as a statistics lecturer in the School of Statistics and Actuarial Science at the University of Witwatersrand since 2015. She has also played a major role in her department, introducing a new course in multivariate data analysis at third-year level. And she now lectures multivariate data analysis to both third and fourth-year honors statistics and actuarial science students. So today, Dr. Raeesa will be talking to us about aspects of biplots in multidimensional visualization. Over to you.
Thank you. Thank you so much, Star, and for everyone else, the organizers and also the attendees for making the time to be here today. And as Star has mentioned that I'm going to be talking about biplots. So I come from basically two universities. I lecture at the University of Witwatersrand, but most of my research is done at a center in Stellenbosch, which is another city in South Africa. And this is our website if you interested in looking at the different projects that we work on. And it's mainly on multidimensional visualization. And today I'm just going to be talking, giving an introduction to biplots, what they are, how are they constructed, an interesting application, and also part of a project that I'm currently working on. So what are biplots? They are just a scatter plot, but we are providing for a high dimensional data set. So typically in a scatter plot, we have two variables. Now in high dimensional data, you have a set of p variables, and you need to visualize this in a two-dimensional space. So essentially that's what a biplot does. It takes the approximation of a p-dimensional data set and approximates it into 2 dimensions. So you're able to view samples and variables at the same time. And that's where the word bi in biplot comes from. You're representing two modes, you're representing both samples and the variables in a data set. And it was first introduced by Gabriel in 1971. And he's had it that the samples, the n samples, were represented by points, and the p vectors or the p variables were represented as vectors. So what you see here is a standard PCA biplot, where we have the blue points are the samples and the green vectors or lines are your variables. And we can use the scatter plot or this biplot just as we use any other scatter plot by reading off values on these axes. So how is it constructed? So the simplest type of biplot is called the PCA biplot, the principal component analysis biplot. And there are many ways of representing the samples in 2 dimensions, such that the actual interpoint distances in the p-dimensional space, so in the high dimensional space, are approximated. And we approximate this, this data set using the singular value decomposition, so the SVD. And what we have is a data matrix X with n by p, so there are n samples and p variables. And we are then using the decomposition to get the matrices U, D, V prime. Now the dimensions of the D matrix will be Q by Q, and Q is the rank of X. So we are now taking a p-dimensional space, p-dimensional data, and then approximating it into 2 or 3 variables. So we then use the Ackermann-Young approximation, which is just taking the first R, and the first R is, typically 2 or 3, as I said before. So you want to visualize this p-dimensional data in 2 dimensions or 3 dimensions, so R will be 2. And the rest of this D matrix it's a diagonal matrix, so consisting of singular values. So the rest of the Q minus R on the diagonal will be replaced by 0. So you have this data set, a very basic data set, 3-dimensional data, variables x1, x2, and x3. And the red points are the 25 samples. And what this approximation by Ackermann-Young is doing is it fitting a plane through these red points such that the distance between the red points and this plane is a minimum. And so each of those red points are then projected onto this plane, which are the blue points, and they projected the distances between the points and the plane is a minimum. You're trying to minimize that distance. So this plane that's in yellow is going to be put flat, and that will represent your 25 samples, which is basically the first 2 principal components. So to represent the n samples, as I said, biplot, there's 2 things, representing samples and representing variables. To represent the n samples, you will then have those projections, so you're putting it flat. And these are then the 25 samples, which are just the rows of our X matrix multiplied by the first 2 columns of the V matrix. Then the second part is to represent the variables, and the variables are vectors, and they are just the columns of V, or V prime, or V transpose. And the V and in both cases come from the singular value decomposition, so UDV prime, and both are used in representing the variables and the samples. So what we see here are the variables x1, x2, and x3, but they are not calibrated with any marker points as you see in a scatter plot. So the next part is to then calibrate these vectors. And the way to do it is that you go in the p-dimensional space. So this is just for variable x1. And you say in the p-dimensional space, and for a certain value of x1, so say mu, you construct a normal plane, and you then find the intersection between the normal plane and your biplot plane, which is the yellow plane, and find the intersection at that marker point of x1. So that's mu, and then a second marker point for x1, you construct your normal plane and you find the intersection between the normal plane and the biplot plane. It's again given by that yellow line, and you continue for as many marker points that you want. So what happens then on your biplot plane, you're going to have a set of intersection lines, and the biplot axis for a variable x1 will be a line that goes through these yellow lines that are orthogonal, that will be orthogonal to these yellow lines. So it will just basically go straight through, and such that it's orthogonal to each of these yellow lines. And then you can do it for all your variables. And then what you'll end up with is a beautiful biplot where you have all your samples and all your variables represented. you can then read off values for each of your samples. So if you want to read off, as in a normal scatter plot, if you want to read off for this point, you are just going to orthogonally project onto each of the axes. So for x2, it's going to be around 7.5. So this value predicts 7.5 for variable x2. And again, if you want to do it for x1, orthogonally project, so it will be 5.5. And that's essentially how we can use a principal components analysis biplot. And that's exactly what I mentioned for prediction. So lucky we don't have to do this by hand, and we don't have to create functions. So we recently published a package in R that is available on CRAN, and it's called biplot EZ or EZ if you're American. And so that's where you can get it. So you can directly download it on the CRAN or within your R Studio. And it's also available on GitHub. So as it's a new package, there may be errors, and the more users we get, if there are any issues, then you can create issues or post those issues on GitHub for us to see. So I decided that since, well, this is a women's conference, I try and look for an interesting example online. And I was lucky to find this paper that was recently published in August 2023, which is looking at the health risk associated in pregnancy. And these authors wrote on machine learning based maternal health risk prediction, a model for the Internet of Machine Learning framework. And their goal was to just, well, what they did is they tracked women and collected a whole lot of blood pressure readings, blood sugar levels, body temperature, heart rate, and they ranked them according to a low to high risk. So they carried on these devices on them, and this device could then in real time collect all this information. And the goal was just to improve maternal health and reduce the mortality of both mother and child. So there were a few variables, 6 we have here, and then there was the categorical variable. So this was the age of the woman during the pregnancy. They took some blood pressure measurements, their body temperature, their blood sugar levels, and their heart rate. And they ran this through a machine learning model, and then labeled these women as either a high risk, having a high risk pregnancy, a mid risk pregnancy, or a low risk. So I fed this all into a standard PCA biplot, and I received this results, which is a lot to take in first. But the first thing is the sample. So we have high risk, low risk, and mid risk, which are colored according to where they belong. And so all the red are basically the high risk. At first, there's not much, as expected, much clusters happening here. It seems all over the place. So looking at the samples, then looking at the variables. So there are my 2 blood pressure variables. And as expected, they will be highly correlated. And this is biplot is very insightful because it's showing me that these 2 variables are reacting the same way, and they're quite close together, and they behave opposite to what, heart rate has no effect on those 2 variables. And then the rest of the variables, we have 8, which ranged from around 70 to around 7. So those are actually 2 outliers that I found in the data, because there was a 7-year-old and a 10-year-old that were pregnant, and also close to a 70-year-old that was pregnant. So it helped me identify the outliers in this data and help me identify the variable relationships, and then also the sample and variable relationships between in this data. So then I separated all the high-risk patients, or all the high-risk mothers, and look at the correlation matrix, because essentially that's what PCA is doing. It's understanding the underlying structure of the covariance matrix or the correlation matrix. And I see that there's a very high correlation between systolic and diastolic blood pressure. And when I remove the other samples and I just have the high risk, then those two are highly correlated. So they're even closer than before. The other variables have shifted ever so slightly. There seems to be just a set of women that just have a certain value for their diastolic and systolic blood pressure. So that would be interesting to look at these women here that have that reading almost exactly the same. And then I removed all the others and just put only the mid-risk mothers, so medium, and you see that the correlation has dropped significantly and it's showing a different trend. Also, what the biplot is showing me is how variable each of the variables are. So how much variance is occurring in each of the variables. If you look again, so if you look now at blood sugar levels, the range lies from there to there, whereas in some other variables would be shorter. And then looking at lastly at the low risk, again, then it somehow jumps the correlation, so 0.804 back to like the normal high risk, and also giving me a different type of biplot. And I've highlighted here and with the green circle that these are patients, or these are women that are very old, that are pregnant, and they've been put into a low risk category. So there could be some anomaly in this data, probably a mistake or a typo in capturing the data. So it's giving me this insight to the data by visualizing it in one setting, and that's the beauty of having a biplot. Since diastolic and systolic blood pressure was very highly correlated, so I removed the one because if one is suggesting something, then the other will suggest the same thing. So I removed that, and then my biplot changed completely. Again, I'm seeing these linear trends, so certain values of the systolic blood pressure. What's nice is that I can see some clustering happening. So between the low level and the mid level, they seem to be all over together. But most of the high risk mothers are further on to the systolic, the higher systolic blood pressure. And it seems like age is not a factor as we would expect. Because whether you're young or you're older, you're still somehow classified as a high-risk mother. So this is a very exploratory, analysis. I didn't go very deep into it, but it would be interesting interesting to go more deeply into understanding the type of data that they've collected and how they've collected it. And then also look again at the type of machine learning model that they fitted. Was it feasible for this type of data? So this is another type of biplot. It's called the canonical variate analysis biplot, and I've applied this to a different data set. And this is the current research that I'm working on. So previously we saw the PCA was with the singular value decomposition. This is using the generalized singular value decomposition. So the limitation in a CVA biplot is that the number of observations needs to be larger than the number of variables. And if you have more variables than observations, then the CAVA biplot does not work. And so I developed a method, I'm hoping to publish this paper soon, which uses the GSVD to then allow for cases when we have large number of variables or larger number of variables than the number of observations. And there are many, many types of this type of data. Lots of cancer data sets are based where P is larger than N. And this is an example where looking at colon cancer gene expression data. So there are 62 cases, so N is equal to 62 and 2,000 genes. So P is equal to 2,000, and you won't be able to construct a CVA biplot using this data set. So using the GSVD, or using the biplot based on the GSVD, I'm able to then, with some heavy maths, able to then create a biplot which looks like this. Although I haven't represented the variables here, well, there are 2,000 variables, so you can select the number of variables that you want here. But what this is showing is that I can see a nice separation between the abnormal and normal. And there are some anomalies, like this one is classified as normal, but it's clearly sitting in the abnormal group. This one maybe also, and then also looking at those two outliers. So it's really given me great insight into the data that I have, and also being a very large data set, it's biplots have given me that the benefit of visualizing it in a lower dimensional space. So to conclude, data visualization is a means to communicate statistical results. So interpretability of the visualization is of great importance. And biplots, although developed in 1971, have really emerged as a valuable tool for visualizing high-dimensional data and providing insights to really complex relationships between samples and variables. And although I only spoke about the PCA biplot, there are several types of biplots, and they all constructed in a very unique way, and they all have different applications and interpretations to use. So our biplot easy package currently has the PCA biplot and the CVA biplot, but there are tons more other types of biplots in the literature that's quite valuable as well. Thank you so much for listening, and I'm open to any questions or comments.
Thank you so much, Raeesa. That was a very, very interesting talk. Do we have any questions from the audience? We have a lot of time for questions. Okay.
No questions.
Yeah.
It's probably too early to some people as well.
Thank you so much, Raeesa, for the great talk. That was really, really insightful. I actually learned something. I've heard of this, but this is a great visualization technique that one could use. So would you say, I have just one short question.
Sure.
Comparing it to other types of visualization techniques, is there some advantage or some disadvantage? Like, what are the advantages and disadvantages compared to other visualization techniques?
So you're trying to approximate the data through this linear plane, right? So you're sitting in a p-dimensional data, and you're then finding this biplot plane, and I would think that the biggest limitation is sometimes that biplot plane, it's linear, and your data is not linear as you know, as data is in the real world. So I suppose that's a limitation to some of the basic type of biplots. But then, as I said, there are many other biplots that cater for like the non-linearity of the data. Another limitation I would think is that you're trying to account for, so you have p dimensions, p variables, and you're trying to account for all of the variation in this p-dimensional space in 2 or 3 dimensions. And sometimes you cannot account for, like, say, 90% or even 80% is good. You account for much less of the variability in the data because you're approximating in such a small space. So you lose some of the variation in the data. And so that's one of the limitations, that possibly you have to look more deeply into the variables that you're considering, the relationships between the variables, and so on. Yeah. But basically, for every type of multivariate technique, so like PCA, linear discriminant analysis, factor analysis, canonical correlation analysis, there is a biplot that you can construct from that. So you essentially a lower dimensional plot that you can construct from these multivariate techniques. Yeah. Okay. I hope that answers your question,
yes.
Star.
Yes. Thank you. Thank you so much, Raeesa. I really enjoyed the talk, and I'm sure that others did too. Thank you so much for your time.
Thank you so much, everyone.